All right, guys, welcome to lesson 4.5. We're going to show you a way that quadratics are used. Quadratics, you may notice, they get a lot of attention. You guys should have heard about them in algebra. You should have heard about them in algebra 2. And now you're going to hear about them again here in pre-calculus. And why is that? Well, they're actually a very useful mathematical function. They're used a lot. And one of the functions that they're used for most of all is modeling these things called projectiles. A projectile is basically anything that is launched, and then after that is under the force of gravity. And you guys can kind of just visualize this. When you throw something, what kind of a shape does it make? Well, it kind of ends up making a parabolic shape, a parabola. And so you can use quadratics to model the path of travel for projectile objects. And so that's what we're going to be doing today, is we're going to model the height of an object that is a projectile. We're going to use what we know about quadratic equations and parabolas to find the maximum height that that object will reach. And then finally, we'll also look at how we can find how long it would take the thing to land on the ground as well once it's thrown. So these are just some of the ways that quadratics are used in physics and whatnot. So once again here, what is a projectile? A projectile is an object that's falling under the influence of gravity. So all three of these pictures below are examples of projectiles. So there's that. Now, here's the projectile motion. It says problem. I guess I should have put formula. It's really more what it is. It's not a problem. So the projectile motion formula is this. Okay, so let's talk about what all these parts represent. This number here, it comes from the force of gravity. So the negative 16 comes from the force of gravity. It's something that they have in physics. It's something to the effect of like I believe that the force due to gravity, well, it's really just the acceleration, but I like to think of it as a force. There's a slight difference there, but it's the acceleration due to gravity, and the acceleration due to gravity is about 32 feet per second squared. And what that means is that every second the object starts falling 32 feet per second faster. And the reason why it's negative is because gravity pulls things down. In mathematics, we model downward direction with negative values. Now, why is it 16? Well, it has something to do with calculus. The force due to gravity is negative 32 feet per second squared, but in the process of creating this formula, that 32 gets cut in half and you end up with 16. Now, that's not stuff that you really need to concern yourself with too greatly, but there is a reason it's there. Now, just as you guys can imagine also, that number will be different if you're on the moon, for instance, because on the moon, the force of gravity is weaker. So that number would actually end up being smaller on the moon. So depending on what planet you're on, the force due to gravity will be different. But on Earth, it's negative 32 feet per second squared, and so our projectile motion formula looks like this. Okay. Now the T represents time. And it's always going to be in seconds. Okay? Now we could change the formula, but if I change it to something else other than seconds, then that's going to change what the 16 would be, because remember that number comes from the number negative 32 feet per second squared. So if we change it to a different time unit, that's going to alter that number. So just so you know, we're not going to do that. We're going to leave it as seconds. So just know that that T represents time. This number here represents the starting velocity. Now, velocity is a lot like speed, okay? So basically what it's saying is if you were to throw an object up in the air, the starting velocity would be just how fast it was going when you let it go. How fast did you throw it? Okay, So that's what I mean by starting velocity. Now, velocity is different from speed in that it can be positive or negative. Positive means it's going up, negative means it's going down. So if you were to throw an object upwards, well, then it would have a positive velocity. But if you were to throw an object down really fast, like you just chuck it down, well, that would have a negative velocity. So velocity is the same thing as speed. The only difference is it could be positive or negative depending on which direction you're throwing it. Okay, now pretty much every problem I'm going to be giving you guys today, we're going to be talking about throwing objects upwards. And so it's going to be positive, but just so you know, it can be negative, meaning you're throwing it downwards. Matter of fact, if we just take a minute here and go back to this previous slide, in these two examples here, in both cases, you would have a positive starting velocity because in both cases, somebody's throwing the object upwards. Now, in this case, if the person's throwing the ball down the cliff, that would be a negative velocity, starting velocity. However, what if they're not throwing it? What if they just let it go? What if they just let it drop out of their hand? Well, in that case, the starting speed is 0 because you're not throwing it. You're just letting gravity pull it. And so it starts from a speed of 0 if you just let it go. But if you chuck it, then you're actually adding a starting velocity to it. So throwing up is positive. That's an interesting statement. Throwing up is positive. Anyway, throwing up gives you a positive velocity. Throwing down gives you a negative velocity. And just letting an object go is a 0 velocity. It's not positive or negative. Anyway, let's go back to our last slide here. So, lastly, we have this, and that's our starting height. Starting height. Now, notice that that little h has a little 0 next to it, and so does the v over here. In physics and in mathematics, a lot of times when we put a little 0 next to a letter, that means it's the starting amount. So this is the starting velocity, and this is the starting height. So in other words, how high up were you when you launched the object? Okay, because what this function does here, matter of fact, we should name this as well, is this tells you the final or the output height, the height at time t. So, in other words, this is a formula where if you plug in a certain time value and calculate it, this formula will tell you how high up the object is at that point. So, got a lot of writing up here, and I'm going to clean it off now. So if you need to write stuff down, you might want to pause it. But here it is. If you know that what your starting speed is and what your starting height is, then you can create a projectile motion formula where after you've thrown the object, you could plug in 3, and what that will tell you is after you plug in 3 and you solve it, it will tell you how high the object is after 3 seconds. That's what this formula does. It's a formula that will tell you the height of an object at any given time. Okay, but you need to know 2 things to have a full formula. You need the starting speed and you need the starting height. This you'll just know automatically because it doesn't change because we're on Earth. Now, if you wanted to move to a different planet, it would be a different number. I guess that brings us to one final thing I'll say about this formula is that it's always in feet. So you might want to add that on your notes as well. Now, we could change it once again to be yards or meters or inches, but if we do that, that's going to change this. Because this, once again, this came from the number negative 32 feet per second squared. So everything that we're doing is in feet or seconds, and I'm not going to change it. We're just going to keep it at that. So feet and seconds are our units for this problem, all right? So now continue to look at this. If an object is launched from ground level, then what do we know? We know that its starting height would be 0. We're going to look at some word problems today where they're going to say an object is launched from the ground. And that's not something to ignore. When they tell you that an object is launched from the ground, that means we're going to put a 0 in right there in our formula. Or since it's a 0, honestly, you can just leave it out because when you add 0, it doesn't do anything, right? So we can just leave it out. Next, we have when an object lands on the ground, then that means its final height is 0. So the output height, not starting height, but the output height is 0. So in other words, we're going to look at questions later on today where they're going to say, how long does it take to land on the ground? Well, what we're going to do is say, okay, well, I know that the output height is 0 because the object has landed on the ground. So I'm going to plug 0 in for my h of t, and then I'm going to solve for t to find out when that happens. So two little things that you need to be aware of today and watch out for. If it's launched from the ground level, that means we're going to plug 0 in for h of 0. If they tell us that the object's landing on the ground, then that means we're going to plug 0 in right here for the h of t. Okay? So keeping those things in mind, I think we're ready to go ahead and jump into an actual problem here. Okay, so here we go. Example 1. A bullet is fired straight up into the air from an initial height of 6 feet with an initial velocity of 900 feet per second. Write a quadratic function to model this bullet's height. Fair enough. Okay, so we have our little formula here, right? We have the height is equal to negative 16 t squared plus my starting velocity times t plus my starting height. All we really need to get a formula in play that's useful to us is we need a v naught and we need an h with it. We need starting velocity and we need starting height, and they've given us both of those. Here is my starting velocity. One way that you know that's your velocity is because they actually just say that here. But another way you can tell is by the units. Velocity is always in distance over time, so it's feet per second. Okay? And then we have our starting height here. So you guys can imagine somebody holding a gun up in the air, and that gun is 6 feet up in the air, and then they shoot it. And when they shoot it, that bullet, as soon as it leaves the nozzle of the gun, is traveling at 900 feet per second. Okay? So that is the two things that we need to know to be able to write a complete formula, and that's what we're going to do now. So let's do it. So the height at any given time is equal to the acceleration due to gravity times t squared plus the starting speed, which is 900 feet per second squared, times the time plus the starting height, which is 6. So basically all I did was I plugged this number in for the v0 and I plugged this number in for the h0. Okay, and that's it. I've got a formula. Now I have a formula where I can plug in any t value I want to, and it will tell me the height of that object at any given time. Okay, so if you wanted to find out how high the bullet is after 5 seconds, all you have to do is plug in 5 for the t and simplify it, and you'll know how high up the bullet is. Okay, and we're going to do stuff like that a little bit later, but for now, we just want to make sure you know how to write the formula. And so the fast answer to it is plug in your height, plug in your v to the formula on the last page, and you'll be done. Straightforward. Okay, let's go ahead and jump into student practice here. So pause the video here and see if you guys can write the projectile motion formula for this problem. And when you unpause the video, you will see the solution. And there you guys have it. So the starting speed is 50 feet per second for the starting velocity. I may accidentally use the word speed. We're supposed to say velocity, but it's because they're so closely related. If you guys ever see me put speed in there, just go ahead and put that in for velocity, but technically velocity. And then we put the 3 in over here. Now, just as a note, once again, I don't plan on giving you guys too many questions, or maybe not even any questions where the velocity is negative. But just remember, all these problems, the velocity I'm giving you is positive. Why? Because we're throwing the object upwards. This is a water bottle rocket, right? And that's obviously going to shoot up into the air. So it has a positive starting velocity. Technically, though, pay attention. You might end up with a problem when they say they're throwing it down. If something's being thrown downwards, you're going to make your velocity negative. So for instance, if I were telling you this was a bottle rocket, which for some reason was being shot down a hill or something, well then you would change your 50 here to a minus 50. In the same way, your height, your starting height, that's usually going to end up being positive because if you're usually on the ground, right? And then you launch it from, maybe it's like from your arm's height or something like that. But isn't it possible to have a negative height? It is if you're sitting in a hole in the ground, right? Like imagine you're like a soldier in a war, and you're sitting in a ditch, right, for protection, and you're launching something from underground. Well, at that point, you would have a negative starting height, and you would need to know that in order to make sure that your projectile reaches its target, right? Now, of course, soldiers aren't calculating things like this, but the designers of the weapons do. So, let's go ahead and move on here to example 2. So I have the same problem here. You guys will notice it says a bullet is fired straight up into the air from an initial height of 6 feet with an initial velocity of 900. So I'm just going to write that formula out again, but we've already done that. That's nothing new. But what I'm going to start doing now for the next 2 examples is I'm going to show you what we can do with this formula now. What are some of the things that this formula can do for us? All right. Well, basically, this formula can tell us a few things. Using this formula, we can find out how high the bullet goes, what's its highest height. We can also find out when does it land on the ground. You can also figure out what is the bullet's height at any given time. And as a matter of fact, I think I'm going to add that question in, and it's not in the notes that you guys printed out, so you might want to add that in now. I'm going to add a new question. What is the bullet's height at t equals, let's just say 3. Okay? I'm going to put a second there just so that we know we're dealing with 3 seconds. So in other words, some guy's got a gun. He's holding it 6 feet up in the air. He shoots it straight up into the air. The bullet leaves the nozzle of the gun at 900 feet per second. And my question to you now is, how high up will that bullet be after 3 seconds? Well, let's go ahead and calculate it. Here's how you do that. You're going to plug 3 into the t value for time, because this is a time, right? So we're going to plug 3 in for the t. And all we have to do is simplify it. Okay, so exponents are first, right? So I'm going to do that. That's going to be 9. So we have negative 16 times 9 now. Next, we're going to multiply. I don't know if I can do that mentally. I think I'm just going to go ahead and use a calculator so I don't want to get it wrong. So 16 times 9. Now it's a negative 16. So it's going to come out to be negative 144. And then 900 times 3 is 2700 plus 6. And so now I'm just going to add all 3 of those numbers together. So I have 2700. And then I'm taking away 144 because it's negative. Then I'm going to add 6 to that. And I get 2,562. And that's feet. The question was, what's the bullet's height after 3 seconds? Well, this is a formula that can tell me the height at any given time if you just plug the time in. So I plugged in 3, and I end up with 2,562 feet. So that would be the height of the bullet at that point. Now I just want you guys to be aware, the height of the bullet would probably be less than that. In fact, it might even be significantly less than that. And the reason for that is because this formula does not take into account things like air resistance, which will slow the bullet down. But we're just, saying, let's imagine we live in a world without air. Where would it be, right? Which is kind of a weird thing to do, but that's kind of how math is. If we tried to factor in air resistance, it gets so complicated. It's outside of our scope of knowledge right now. So let's not worry about it. Just showing you guys what quadratics can be used for. But in real life, you would have to temper this number somehow by factoring in air resistance. But there it is. All right, let's go ahead and take a look at part B now. Part B is asking us, how long does it take this bullet to reach its maximum height? Well, maximum height is here, right? So let's circle that on our notes and let's label that as the max. Now, in case you didn't recognize that, so now the vertex, as we said before, is a point with the coordinates h and k. And in this case, instead of, h is the input value, which is the x-axis, and k is the output value, which is the y-axis. But understand that when we're dealing with this, h of t, the x really means t, and the y really means h. So t, the x-axis is time, the vertical axis is height, and so in this case, the h is this is kind of confusing because we're using, let me use h of t here. This h doesn't mean height. This h is the x part of the vertex, so that's actually going to be a t value. That's a little bit confusing. So to keep it from being confusing, instead of using h for this, I'm just going to put t here instead. And then the k part, which is the y value of your vertex, is the height. So I'm just going to go ahead and put h of t here. So the max is is located at the vertex, and specifically the maximum value is the height, or the y value at that point. Okay. Now part B is asking us, how long does it take to reach the maximum height, and that would be the t value. So if they ask what's the maximum height, they're asking for the y value. If they're asking for how long does it take to reach the maximum height, like on part B, they're asking us to find the x value, or the input value for the vertex. So we know how to find a vertex. We did that last week. So let's go ahead and do that. To find the x value of your vertex, which in this case is a t, we're going to use the old formula, x equals negative b over 2a, right? That tells us the x value of our vertex. I'm going to write that formula back up here at the top really quick. And so my b value is 900, so I'm going to write 900 in here. And my a value is negative 16. So what I end up with is negative 900 divided by negative 32, which I'm going to need a calculator for. And don't be surprised, with these types of problems, you are going to get ugly looking decimal numbers a lot of times. It's not uncommon. Just because in real life, we don't end up with nice, neat numbers a lot of times. They come out kind of messy looking. So 900 divided by 32 is 28.125. And remember, what I just found was a t value, so that's 28.125 seconds. So what that means is that's how long it takes that bullet to reach its maximum height, 28.125 seconds. Now in real life, it would probably reach its maximum height a lot sooner because of air resistance slowing the bullet down, so it wouldn't be able to travel for as long. In this case, with this model, we're just looking at just gravity's effect on the bullet. So if you can imagine a world without any air, it would literally take 28 seconds for that bullet to stop going up and then start coming back down. Okay. Now the next question is, what is its maximum height? Well, this is how you find the x value of the vertex, which tells us how long it takes to reach the max. But if you want to find its actual max height, that means we need to find the y value. And how do you do that? You take this answer that we got for t, for the maximum height, and we plug it in to our function here. So I'm going to be plugging in this number, and so it's a pretty nasty number, and we're going to basically be doing a whole lot of calculator work. Even though the numbers are ugly, the good news is that the calculator is going to do all that work for us. So it's not a huge deal It's just kind of annoying to have to write all these numbers. Okay, so let's go ahead and do it. The order of operations, though, is still exactly the same. The first thing we're going to do is we're going to square this number here. So let's do that on the calculator. So I have 28.125 squared. Oh, didn't type it right again. 28.125 squared. All right, so there's that. Then we're going to multiply it by negative 16, so times 16. And so now I've got this. So by multiplying those two things together, this piece here, I'm going to erase it just for the sake of space, but all that just became negative 12,656.25. Okay. Now we're going to do the next part, 900 times 28.125. So 900 times 8.5, 25,312. So let's replace all that. 25,312. And 6 doesn't need to be simplified. But now we're going to add this number in the middle to the number in the front and then the 6. So I'm going to say plus a negative 12,656.25. I want to make that a negative 12,000. And then we're going to add the 6 also to it. So just basically adding all the numbers together. Okay, I'm going to write that down. I feel like maybe I did something wrong, but I'm going to write it down really quick. 12,662.25. I just want to make sure I did something right. No? Okay, we're good. All right, so there it is. And so what this represents is how high the bullet is at 28.125 seconds. And that would be the top spot here. So that's the maximum height. So let's review a little bit. We did 3 things. Part A, I just asked you simply, what is the bullet's height at t equals 3? To get that, I just plugged in 3 for t and I solved. For part B, I asked you, how long does it take the bullet to reach its maximum height? Now, you might want to write down here, this is the x value of the vertex. When they ask you how long it takes to reach the max, they're basically just asking you for the x value of the vertex, and then you can also write down this little formula because that's what you do to get it. Okay? And then part C is asking for the maximum height, which is the y value of the vertex. And you get that by plugging in your answer from part B to the projectile equation. Okay? So, there you have it. That is how you can find the height at any given time, how you can find how long it takes to reach the maximum height, and also how long or what the actual maximum height is. So, here was your guys' problem, and as you guys may recall, your formula for that you should have gotten was as follows. So that's the formula you're going to use to answer these questions. But before you begin, I want to throw another question in here for you guys. I want you to find the height at t equals, I'm going to say 2 seconds for you guys. So find the height of the bottle at t equals 2 seconds. Okay? So go ahead and pause the video here. Work out as much of this as you can. And we'll go from there. Okay? All right, so here's my setups and here's my answers. So if you wanted to find the height at t equals 2 seconds, that would be 39 feet. If you wanted to find how long it takes to reach its maximum height, you use your negative b over 2a formula, which gives you 1.5625 seconds. Now I want you to notice something, that I asked you to find the height at 2 seconds, the maximum height happens at 1.5. So here's the maximum height. So that's going to be at about the time value of 1.5. Okay. But I asked you up here in question A to find the height at 2 seconds. So when you're finding the height at 2 seconds, you're finding the height after it's already reached its max and is coming down a little bit already. So keep that in mind. Not significant, just kind of interpreting your results for you a little bit. The last part here, maximum height, we plug in our time value from part B into the H function and calculate it. I end up with 42 feet, which makes sense. It should be a little bit higher than the answer from part A, because in part A, the bullet's already reached its max height and then it started to come back down a little bit. So I'd expect the answer in part A to be a little bit lower than the answer in part C, because C is the maximum height. Anyway, so there's that. Now we're going to move on to a new question here. What else can we do with these things? Well, we can, like we saw in the last slides, you can find how long it takes to reach a certain height. You can find what its maximum height is and when that happens. But another thing you can do is you can find out when it actually lands on the ground. Now, whenever you're trying to find where something lands on the ground, I'm going to write the word ground here, but in mathematics, when it touches the ground, which is really the x-axis, what you're finding then is the roots. And we learned how to do that earlier in this unit. How do you find the roots? Well, if it's in standard form, you use the quadratic formula. So we have h of t is equal to negative 6t squared plus, for me, this is the 900t plus 6, because we're talking about that bullet, right? Okay. So we're going to plug it into our quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now why does this work, though? Before I go any further, I realize I kind of got a little bit ahead of myself. Let's talk about it a little bit. If we're on the ground, what's the height? The height is 0. So I can plug 0 in right here. You're only allowed to use the quadratic formula if you have a standard form quadratic that's equal to 0. And the projectile formula is in standard form already, and it always will be. The 0 is here, though, because we're asking when is it landing on the ground. When is the height equal to 0? And so what we're going to do is we're going to be finding the t value, the time, where it actually does land on the ground. So since we're looking for where it lands on the ground, we plug in 0 for h of t, which means we're set up perfectly to do the quadratic formula. So let's go ahead and do that. So plugging in the 900 first. Plugging in the a next. And then finally the c. All right, so when we simplify these quadratic formulas, like I've told you last time we did it, I always start by doing these 4 groups first. Let's go ahead and do that. So I'm not going to show my thinking as I go through. I'm just going to do that. So that's what you get if you simplified all those 4 parts. The next part I will show my thinking, though, for, because I want to relieve you guys a little bit. First of all, we're going to add these together, right? And so if I add those together, then I'm going to end up with negative 900 plus or minus the square root of 810,384. No, I'm not going to ask you guys to break that down by hand. There's no point in it. It's not even helpful if you do it. You end up with an answer that's not very meaningful anyway, although it may be correct. We're just going to use a calculator, okay? So let's do that. Make some space here, though, so let me erase all this from earlier. And I'll just show you guys what to do here. We're just going to let the calculator do that work for us. So I'm going to do 810,384, and I'm just going to push my square root button, and there it is. So it's 900.2. And I'm just going to round it to the tenths place because that decimal never seems to stop. So it's 900.2. No, I'm not going to break down the square root. take out the pairs like we did last time. You need to know how to do that stuff also for your test, because some of the answers will be written in that form. But when we're doing these projectile problems, just use a calculator and round your answer. Okay? And then we're going to split this up into two problems. We're going to do one where we do negative 900 minus 900.2 divided by negative 32. And then we're going to do another one where we do negative 900 plus 900.2 over negative 32. And then we're just going to use our calculator to do both of these problems at this point. Okay? So, of course, you're going to do the adding in the numerator or subtracting in the numerator first, and then you do the division. So, let's go ahead and do that. So, here's our answers. But let's interpret them, because this is a word problem, and therefore these numbers mean something in this word problem. These are the answers to the question, how long does it take to land on the ground? And so the answer here is 56.2 seconds. Now that's the only meaningful answer that we have, and that's the answer. So once that bullet is shot, it goes up in the air, it reaches its max height, and then it lands on the ground. That takes almost an entire minute to happen. Now remember, in real life it might be a little bit different because of air resistance, but that's our answer for now, okay? Now what's up with this answer though? First of all, it's negative. There is no such thing as negative time, so we can ignore that. Why does this happen? Well, because when we do math, we have to think about what our answers mean. The math doesn't think about what our answers mean. It just tells us the answer. Why is that? Well, it's a little bit hard to see here, but remember the starting height was 6 feet. So this dot here, it looks like it's at the origin, but it's really actually a little bit above the origin because the bullet was fired from 6 feet above the ground. It's kind of hard to see that that's 6 feet, but the reason why is because remember our maximum height? It was something like 12,000 feet, wasn't it? So if this is 12,000, you can imagine 6 feet is going to look like it's right on the line, but it's not. It's actually a little bit above the line. And so it has to, the graph actually keeps going, and it does hit the x-axis behind this vertical y-axis as well, and that's where it hits it at. So the reason that number is there is because the math gives us a parabola, which does touch the x-axis in two different places, and these are the two places where it touches it. However, the one that we really care about is this one. This doesn't even exist. The bullet doesn't ever really touch the ground over here. That's just hypothetical because the formula gives it. So, long answer short, you're going to get two answers, but get rid of the negative one and keep the positive one, okay? That's the one that tells you how long it takes for the bullet to land on the ground. So let's review. A bullet is fired straight up into the ground, or straight up into the air. You have a velocity and starting height. How long does it take to land on the ground? Well, what you do is you take the h of t and you put 0 there, and then you have a quadratic equation in standard form equal to 0. So the way that you find how long that takes is use the quadratic formula, and you're just going to use a calculator to get your answer, because a lot of these numbers are going to come out looking weird. So go ahead and try yours once again. Once again, I'll remind you what your quadratic equation was that you guys have been working with. Yours was negative 16t squared plus 50t plus 3. Okay, so go ahead and see if you guys can find out how long it takes to land on the ground. Pause the video here, and when you unpause it, you'll see the solution. All right, so final answer is 3.25. Now, here's your quadratic formula for plugging in your numbers, and then here's my steps for solving it. Notice the double negatives become positive, right? So you end up adding the 2500 and the 192 to get 2692. Square root the 2692, you get 54.4. If you do negative 50 plus 54.4 and divide by 32, you get negative 0.1. If you do negative 50 minus 54.4 divided by 32, you get 3.25. As we said before, you get rid of the negative answer because what that one tells us is where it touches the x-axis back here, but in our story problem, that doesn't exist. The bottle rocket starts off at this height, and it was never back here to begin with. So the math gives us an erroneous answer, but we ignore it, and we go with the positive one that's on the right side. So this bottle rocket would take 3.25 seconds to land on the ground. Okay? And there's that. Now, that's my last slide, but I want to show you guys one more thing. And you guys are going to be angry at me when I show you this because you're going to be like, Bailey, why didn't you just show this to me to begin with? And the reason why is because I wanted you guys to know how to do this stuff by hand. But I'm going to show you a really cool thing that you guys can do to be able to do this on a graphing calculator. Or actually, in this case, a website, because you guys don't have graphing calculators. Now, if we were in class, I would be showing you how to do it on a graphing calculator, but we're not in class. So, all right, so I think we've done this before, and we're just going to do it again. What we're going to do is we're going to go to desmos.com. Okay? You're going to click graphing calculator. And what you're going to do is you're going to type in the function that we had. So, for instance, your guys' problem was negative 16 x. I'm going to say x squared, though, because Desmos likes x and y. So instead of t, I'm going to use x. X squared plus 50t, and then plus 3. All right. Oh, I put a t in there again, darn it. It's supposed to be x. There we go. All right, so there's my graph. Now, it's hard to see it because the graph goes high, but we have to zoom out to see the entire graph. Looks a little bit weirder, right, than when we had it skinnier, but I can stretch it here. And so now it looks a little bit more normal. Now, right here, you guys can see everything that we were looking at. The initial height is where it touches the y-axis. That's at 3 feet. The maximum height, it reaches its maximum height at 1.5625, I think it was, seconds. And the maximum height is 42 feet. It lands on the ground at 3, I got 3.25, but this is 3.184. Now, why is it a little bit off? This is actually going to be more precise than mine because we rounded along the way, and when we round, we lose accuracy. So it's literally, you guys could do every problem just by using Desmos and looking at the graph and finding the pieces. Now, I am going to ask you guys to be showing work, so I still want you to know how to do it, but I would highly encourage you guys, after you do it by hand on your homework, to come on Desmos and check your work. You could do that on the test too. Even though I'm going to be asking you to show your work, you could really literally just come on to Desmos during your test and type in the function and double check your answers this way. So the y-intercept tells you the starting height, which they usually give you anyway. The vertex tells you when it reaches the maximum height and what the maximum height is. And then finally, the root tells you when it lands on the ground. Okay, there is another root over here, but that's the erroneous one that we ignore, right? Because bottle rocket over there to be started here. All right, anyway, there's that. And you just got to know how to zoom, because like, for instance, if I had put mine in there, mine was 900 feet per second at a height of 6 feet. And that's really crazy because that bullet goes really high. Remember, it reached like 12,000 feet. So you would have to zoom out a lot to be able to see that graph. You can adjust it a little bit just by using 2 fingers and pulling the screen apart. But there's my graph. And where does it touch the y-axis? Once again, it touches the y-axis at 6. That's my starting height. Here's my how long it takes to reach the maximum height, and here's what the maximum height is, and then finally here's the root, how long it takes to land on the ground. So you just have to be able to stretch your graph out once you're on there to get the vision of the parabola that you need. But there it is, nice little shortcut to check your answers. But do understand, if you guys don't show your work on your homework, I'm not giving you credit for it, okay? You still need to work out the problems. I'm just showing you this so that you can check your answers, okay? I still want to make sure you actually know how to do the math to get the answers. And that's the end of our lesson. So, hope that was helpful. We'll see you next time.